Okay, off we go. Here's where we left off last time. We were talking about equations of lines and planes in space. And neat fact that I think is worth knowing and making an explicit observation of and reasoning through. If you have a plane and if there are no oh come on, stylus. If there are no y's in the equation, as a for example. And sometimes this will happen. You'll have an equation. It'll be ax plus cz equals d. Right? No y's in the equation. This very quick little observation about the equation has a powerful conclusion. Your plane is parallel to the y-axis. So I love it when this kind of thing happens. Simple algebraic observation, powerful geometric conclusion. So let's think through why this is. Of course, if there's no y's in the equation, then you might say this is what the y term looks like, right? Instead of having the usual b times y, well, there's no y's, so it would be 0 times y. Now, keep in mind, we have a rule when you have the equation of a plane in that certain form. Those coefficients tell you the normal vector, right? So I now know what that normal vector is for my plane. And it's pretty easily observed that normal vector is perpendicular to the y-axis because the y-axis is in the direction of the vector E2, that is 0, 1, 0. And pretty easy to see that this dot product is 0. That means that these vectors are perpendicular. And now I argue that because the normal vector for the plane is perpendicular to the y-axis, it follows that the plane itself is parallel to the y-axis as claimed. Everybody follow the argument there? Pretty cool result. Everybody's happy. Okay. All right. So you might entertain yourselves by speculating and then proving similar results about what happens when there's no x's or when there's no z's. And it's obviously going to be a very, very analogous argument. The picture is going to be different. Some of the details will be different. Be good little practice problems. Okay. All right. Let's see here. Moving along then. Okay. Here's another puzzle, and again, I'll remind you that when you're talking about lines and planes in space, there are lots and lots and lots of little puzzles of, well, here's certain information, find the equation or a parameterization or what have you of some other thing that relates to the givens in certain ways. Anyway, here we go, another example. So suppose we have a line and we're trying to parameterize, and we know that it goes through a given point A, and that it is parallel to both this plane and that plane. So, all right, it's got to be parallel to that plane, and it's got to be parallel to that plane. All right, and I think you can probably see that given this information, this does uniquely characterize a single line, right? There's going to be exactly one line going through that point that's parallel to both of these planes. Everybody on board? Okay. All right. Okay, so how to find the parameterization? Well, of course, the remaining ingredient that we need for a parameterization is we need this direction vector v. And once we have v, well, we know the point that it goes through, and if we have this vector v that we're looking for that gives the direction, we know how to parameterize lines, and this is how you parameterize that line. So again, that one missing element, how do we find v? Okay, so looking at the givens, this v that we're looking for, let's think this through. The v is parallel to this line. This line is parallel, for example, to this plane. This plane is perpendicular to this normal vector, right? And so altogether then, let's think it through and you look at the geometry. Shouldn't it follow that this vector v should be perpendicular to this normal vector? Everybody good with that? And then likewise, well, it's also going to be perpendicular to that other normal vector. So conveniently, this vector v needs to be perpendicular to two vectors that I can immediately read off from the given equations. I can immediately read off those normal vectors from N1 and N2 from what I'm given. So, good deal then. So I've got these two vectors, and I want something that's perpendicular to both of them, so we use the cross product. And we win. Yes?
How do you know that 110 is perpendicular? Actual slide.
So this is the trick about equations of planes and how they relate to normal vectors. Let me go back up to that. Here it is. The coefficients A, B, C are the normal vector in the equation for the plane.
Okay.
Yeah. Okay. All right. So, so game over if we win. Okay, now these last two examples, I used some geometric, what I'm going to call transitivity arguments. And I want to give you all a warning about these transitivities. First of all, what do I mean by a transitivity? This plane, I argued, was perpendicular to this normal vector, and the normal vector, I argued, was perpendicular to the y-axis. And because of that relationship and that relationship, I drew a conclusion then about that relationship, right? So, P compares to N compares to Y, allowed me to conclude something about how P compares to Y. So it's kind of a transitivity, kind of a connecting the dots, sort of. Down here in this next example, let's see, the line is parallel to the plane, and the plane is perpendicular to the vector, and therefore the line is perpendicular to the vector. So, again, kind of a transitivity. The warning I want to give you is that these sort of transitivities, they don't always work. Just because grammatically it kind of feels like they ought to, it does not necessarily work. And I'm getting a little warning message here. Oh, I only have 2 gig remaining. Okay, where's the go away button? Ignore. There we go. Good. Okay, so looks like it ought to be true, but not. If you have a vector parallel to your plane, right? There's a vector parallel to my plane P. And if the plane P is itself also parallel to the vector W, right? Well, V is parallel to P, P is parallel to W. Doesn't it kind of look, symbolically, wouldn't you, if you were reading this, you'd have this urge to say that V must be parallel to W. But obviously it isn't. It's not even close. Right? So this is a, transitivity landmine that you got to watch out for. The upshot here is when you're making a geometric argument that, has this kind of connect the dots aspect to it, always think it through carefully. And my rule on this is, if you use one of these arguments in, on a homework exercise or on an exam or something, if you make the argument, V is parallel to P, P is parallel to W, and therefore, if the argument, which this isn't, if the argument is correct, if it's a valid geometric transitivity, such as in these previous examples, that's fine. No problem. But if it's wrong, obviously it's not. So you don't have to prove the theorem, right? When I up here, you don't have to prove a theorem that says that plane, vector axis, and therefore, you don't have to prove. You have to state it, and you have to be correct. It has to be geometrically valid. Don't have to prove it. Okay, another example. Here are a couple of planes, P and Q. You can see as I have them drawn here, P and Q are perpendicular, right? And then furthermore, Q and R, also perpendicular. So you would think, again, reading it on the page, you would kind of think, P to Q, Q to R. Okay, wouldn't it seem like P and R ought to have some sort of relationship? But look at the picture and no. They're not necessarily perpendicular. They're not necessarily parallel. There's just nothing you can conclude at all. There's no clear relationship between them. Okay, so again, another transitivity landmine. How we doing? Everybody with me? Yes. Oh, sorry. Yeah, that's all right. My bad. Okay. All right. Okay, let's talk about how to parameterize a plane. Now, this is an example of a more general process of parameterizing a surface. We're not going to get into parameterizing surfaces just yet. We'll do a lot of that later in the course. For right now, it's very similar to something we've already done, and so it's worth talking about this one. A plane being a surface, being what you might call two-dimensional, it's going to require two parameters to do it. And what we're going to find momentarily is that our parameters are going to be S and T instead of just the one parameter we usually use, T. We're going to need the two parameters, and here's how we use those two parameters. If I've got a plane, by which I mean if it's defined by a point in the plane and a couple of vectors parallel to the plane. Note this is kind of analogous to how we parameterize a line. Right? Two direction vectors instead of one. Right? But the big idea then is that those vectors, if I scale, if I scale v by some amount, then that allows me to move parallel to the plane, an arbitrary amount in that direction. And if I scale w, right, that allows me to move in the w direction by an arbitrary amount. And starting with the point A that you're given, dark blue A plus green plus light blue, this is the form that I have here, will allow you to get anywhere you want to get in the plane, right? Wherever you want to get to, whatever point in the plane you want to generate, this formula will do it. So it's, again, a lot like a parameterization of a line. It's just, well, you've got two directions you need to be able to move in instead of just the one. Okay. And you see, of course, we have the two parameters, S and T. Okay, all right. So quick examples. Let's see here. Suppose we have, this is analogous to a problem that we did earlier. We looked at, how to find the equation of a plane containing 3 points. Here we don't want an equation. Here we want a parameterization. How are we going to parameterize a plane going through these 3 points? Well, we're going to start with the same trick we did previously, namely we're going to pairwise subtract. And here's where we had to start thinking about how to find a normal vector and the cross product, blah, blah, blah. Here we don't. We have already now the two vectors parallel to the plane and the one vector, actually I have three of them, but 1 point that's in the plane, and we're good to go. And this parameterizes the plane. Just using the formula at the top of the page there. Everybody good? Everybody see the ideas there? Okay. Alrighty. Okay, so the last thing we're going to talk about in section 1.5 is a category of questions that the book groups together and calls distance problems. And how do you find the distance from a point to a line, or from a point to a plane, or from a line to a plane, or between two lines? There's various different sort of versions of this. I'm going to show you some examples. These will illustrate the kinds of tools that you'll need, and these also will show you some neat tricks. Right? There is a puzzle aspect to a lot of these questions, and I'm going to spoiler. I'm going to show you how the puzzles work, and then all you have to do is just remember, get comfortable with the features of these tricks, and then you can use them whenever you need to, whenever they're convenient. So here we go. How do we find the distance from a point to a line? All right. Well, if you have a point and you've got a line, well, if you have a line, then you can also pick any point that's on that line. This is not the distance I'm looking for, of course, because that's, if you think about it, you're going to talk about how far is a point away from a line. Of course, what you mean is the perpendicular distance, not the, distance off at whatever angle, right? You want the shortest possible distance. Nevertheless, we can take that subtraction, call that vector W. It's not the vector we're looking for. Let's set that aside. Next thing I want to do is I want to look at its projection in the direction of the line. And again, y'all remember projection. That's the whole dropping the perpendicular thing. Well, if you think about it, this gives us the two ingredients that we need to be able to find what I actually want. What I actually want is this vector right there. That difference, green minus blue, right, gives me the vector whose magnitude is the distance that I want. So that's the neat trick. Basically, it's subtract the projection and you win. Everybody happy with that? Okay. All right, now this is one way to do it. Depending on circumstances, this might be the best way to do it. Every situation is different. I am going to show you, though, a second way. This was just the first. Second way to find the distance from a point to a line. And sometimes this might be handy as well. This one seems like a lot more trouble. Like I say, pros and cons. We're going to use a clever argument here that is another sort of example of a larger category. Sometimes when you want to compute something, what you should do is compute something else two different ways. And if you think about it, if you compute that something else that we don't care about two different ways, your results must be equal to each other. And if one of those computations involved the thing that you're interested in, then you can easily solve then. In the algebra, you can solve for that thing that you're interested in. So this is a weird way to compute something, but it's very clever and it's very powerful in a lot of instances. If I want to compute D, I don't have to go directly at it. I can just involve D in a computation of something else that I can then compute some other way and foot in the door and go for it. Okay, so let's go through these two different methods. First, where does this come from? I got the area. Keep in mind we're talking about the area of this parallelogram right here. This is the parallelogram defined by the same W vector we talked about on the previous page and the same projection vector that we talked about on the previous page. So still those same two vectors. So I claim that the area is equal to the height, which is the distance I'm looking for, times the base, which is just the magnitude of the projection. And that's an old geometry formula, right? Height times base gives you area. Not that I care about area particularly, but I can compute area a different way. This time I'm going to compute the same area, but I'm going to do it using a previous formula, namely that if you have a parallelogram with two known edge vectors, then let's see here, P cross W has magnitude equal to that area. Right? One of our cool facts about cross products is the magnitude is equal to the area of the resulting parallelogram. Everybody remember that one? Okay, so we have successfully computed area that we don't care about two different ways. The thing that we're interested in is one of the participants in that equation. Solve for D, victory. Yes?
Why would you want to do it this way over the other way? Because you have to find the projection both ways, but instead of doing vector subtraction, you just have to do a cross product.
So every circumstance is different. It may be that in the circumstance that you're facing, you may have already computed this cross product, perhaps. Something like that. It may be that just from an algebraic standpoint, this formula, that divided by that may have algebraic advantages. Depending on the circumstance, you never really know. Yeah. Right. Okay. All right, everybody's good. Okay, how do you find the distance between parallel planes? Again, when we talk about the distance between parallel planes, which of the many distances am I talking about? We mean the perpendicular distance. This is what we mean by the distance between two planes. Distance off at some angle, to other points. That's just not what we're talking about. Okay, so this is a kind of an easy one. Here's a vector representing a distance that we don't want. This is a non-perpendicular displacement between the planes. But in the direction of the normal, if we just take the component in the direction of that normal, notice that component is exactly the distance that we wanted. There you go. Sometimes it's just one step. Everybody see how that worked? Alrighty. Now this next one is tricky, and reminder, there's a lot of things in this course that are tricky, and in fact tricky enough that I don't think you should hold yourself to the standard of, would I have been able to think that one up on my own? Right? There's just a lot of stuff in math that like some really clever person long ago thought of some really clever idea, and we've all kind of been ripping off that initial clever person for a very long amount of time. Who knows how long? So here's the tricky move. Suppose you want to find the distance between two skew lines, and at a glance it looks like a really hard problem because take a point down here. Which of these possible distances to L1, which one do I want? And worse, what made me pick this point, right? Maybe there's a better one elsewhere on the line. Which one? How do I know which point on L2 I should be looking at? Right? There's kind of two. I got which point on the first line and which point on the second line, and none of this is given. So here's the clever move. When you have two skew lines, neat fact that I'm going to prove in a moment, two skew lines are always contained in parallel planes. So what we're going to do here, and I hope this is a believable pitch, but in order to find the distance between these two parallel planes, the distance between these two skew lines, and again I want the perpendicular distance. Right? What I'm going to do is just find the perpendicular distance between the two planes containing them. Isn't that slick? Again, I didn't think this. Somebody showed me this. Right? So you might not have thought of it either, and now I'm showing you. So, yeah. Okay, so that's the move. How do we find the distance between those two parallel planes? Well, we already know how to find the distance between two parallel planes. Previously solved problem. So all that remains then is how to find these parallel planes in the first place. And this is not that bad if you think it through. A vector parallel to L1 is also parallel to both of these planes. A vector parallel to L2 also parallel to both of these planes. And therefore, if I want to know the normal vector for these planes, I need it to be perpendicular to both V1 and V2, and I have this pre-existing tool for how to find something perpendicular to two given vectors. We take the cross product and we spike the football. Is everybody good? All right. Okay, so that does it for 1.5. Recall, of course, we've already done 1.6. That was our first section. I did them out of order. And now on then to 1.7, talking about new coordinate systems. Y'all already know rectangular coordinates. This is what a lot of people think of as just the coordinate system. for the plane. Start off in the plane. And rectangular coordinates, again, exactly what you think they are. A couple of nice features. Rectangular coordinates are unique. If you give me a point, this point here, right, there is exactly one and only one x coordinate. And there is exactly only one y coordinate to describe that point. Right? No options or, well, you have choices. No, the x and y coordinates are unique. And that's nice. We don't have to worry about whether the XY coordinates that I use and the XY coordinates that you use might be different but equally acceptable or something annoying like that. Here's a nice couple other features. Rectangular coordinates is algebraically very convenient in certain ways. So, for example, I remember this fundamental fact about coordinates. In fact, you can take this as a definition of coordinates, I suppose. But the coordinates for a vector are the coefficients in a linear combination of the standard basis vectors giving that same vector. Right? So coordinates are coefficients. That's super convenient algebraic fact. Okay. And then also, kind of a sort of a generalization of that. If you have a linear combination of any vectors, you can compute the linear combination by just taking the linear combination one at a time in the coordinates. Super handy. So, gotta love rectangular coordinates. Bad news to come. Neither of these luxuries holds for any of the coordinate systems that I'm about to show you. So with these new coordinate systems, you have to, they're going to have certain advantages, big advantages. Right? We're not going to waste your time with something that's purely inferior, right? But they do have big disadvantages as well, and you got to sort of let go of these familiar features. Okay, polar coordinates. Now, I think many of y'all have probably seen polar coordinates previously. If you haven't, don't worry about it. Not a problem. I'm going to say everything that needs to get said. The way I like to think of polar coordinates may be a little bit different from how you might have seen it previously, but I like to think of a function. This is a function, what I'm calling g sub p, that takes two numbers r and theta and returns two numbers x and y, where theta and r perform the following functions. So theta tells you which direction you should go. Theta defines a direction like that, based on moving counterclockwise from the positive part of the x-axis. And then r, I'm going to say, loosely speaking, defines how far you should go in that direction. And if you go that far in that direction, then that gets you to a point. And so I think you can see that, this is a coordinate system in the sense that two numbers can be used to define a location. Everybody good? All right, now I have to talk about the asterisk there. What's the deal with the asterisk? Why is this in quote? Whoops. Yeah, okay, red's good. Okay, why is this in quotes? So the thing is, R might not be positive. R might be negative. There's really nothing wrong with R being negative, fundamentally. And so if R is negative, can you talk about that as being a distance? The word how far suggests a distance, and distances are fundamentally positive things. Right? So I have to put the quotes on the how far. Specifically, if R is negative, the way you interpret that negative is that you use that as an indication just to go the opposite direction. Kind of like what you would expect, I would think. Okay. All right, so this is polar coordinates. And pretty easy to persuade yourself that x is r cosine theta and y is our sine theta. I'm going to leave the details of that as an exercise. You may have already done this exercise. The point is that we've got a right triangle right there, and think about the trigonometry of this triangle, and boom, these results come out. Make sure you can do that. Make sure you're very comfortable with all of that. Okay. All right. Okay, so now let's talk about some of the annoying oddities of polar coordinates. Again, we have a uniqueness problem. If you have a point here in the plane, this is a point in the plane, so x and y are well defined. There's a unique x and there's a unique y describing that point. There's nothing else to talk about on the rectangular coordinates. But here's the thing. You could describe that point in polar coordinates by saying, well, look, whatever this angle is here, I'm going to let that be my theta. And then this point, apparently, I've got it as distance 5 away from the origin. And so then the r coordinate is 5. And so you could say 5 comma theta as your coordinates, your polar coordinates for that point. Okay? Those are acceptable polar coordinates for this point. But check this out. You could also, right, say I'm going to add 2 pi to the angle. And let's think about what happens if you add 2 pi to the angle. If you add 2 pi to the angle, that gets you going the exact same direction in the xy plane, because 2 pi is a full circle. So 5 comma theta plus 2 pi are different but fully acceptable polar coordinates for the exact same point. And there's that non-uniqueness. Everybody with me? Questions? Feel free. Okay, now there's a weirder alternative set of coordinates, and that would be to say, okay, well, let's add just pi. Whoops, missed. Let's add just pi to the angle. That's going to put me going that way. That's going to have me going exactly the wrong direction. Right? This direction is pointing exactly opposite the direction I should go. But the thing is, if instead of going 5 in that direction, if I were to go -5, and keep in mind, negative means go the opposite of the given direction. And so -5 would get me right back to the exact same point. So -5 comma theta plus pi, also acceptable, perfectly acceptable polar coordinates. So polar coordinates has a serious uniqueness problem, and is something you kind of have to always keep your eyes out for. Okay. All right, let's see here. Another annoying feature of having a second coordinate system is now you have to be clear from here on out which coordinate system you're using when you write a list of coordinates. So here 2 comma pi over 6, and if I just casually in doing some work just write 2 comma pi over 6, where is that point? Now a lot of people would say, well, okay, this looks like an angle. So this is probably polar coordinates. It's probably an r comma theta kind of a deal. And so let's see, pi over 6 is like that. That defines this direction. We'll go a distance 2 in that direction, and then altogether that puts me at that point. And well, you could have meant this point. Polar coordinates 2 and pi over 6. But notice what's written here in the box. Nothing about what's in the box actually specifically says that these are polar coordinates. Again, you look at this number here, pi over 6, and you think, well, it looks a lot like an angle, but it's still a real number. And y is perfectly allowed to be any real number. Pi over 6, therefore, could have been y. I mean, it'd be weird, but it could have been a reference to pi over 6 being y, and therefore 2 being x, and so it could be talking about this number, and this is, this point, and this is definitely a different point. than the one over there. So heads up. Be careful when you see an ordered pair. If there's any reason to wonder as to which coordinate system it might be, then look for context clues, or if you're the one writing in the first place, try to avoid in the first place just by explicitly saying r comma theta equals 2 comma pi over 6. Now there's no ambiguity at all. This clearly indicates that these are the polar coordinates, and therefore I'm talking about this point. Everybody happy? Okay. All right. So be careful with that. Another thing to be careful about, a lot of students are a little bit reckless with algebra. Some high schools, I'm not going to name any names, possibly my high school, no comment. In many classes, they just perfectly condoned algebraic mistakes of certain sorts. And it's very dangerous, and you're going to get some severely wrong answers, and your bridge is going to fall down if you're not careful with these points. So in particular, here's a true fact about polar and rectangular coordinates, that r squared is always x squared plus y squared. There's this urge that students feel to, we're almost there. I've almost solved for r. I need to solve for r, and r is the square root of x squared plus y squared. The problem is, square root means positive. Right? If you mean plus or minus, you have to say plus or minus, right? This symbol, right, the usual symbol, means the positive square root. So, issue. So I advise don't solve, because you can't anyway, and it's good to leave it in a form that's unambiguously true. Likewise, there's this urge to use arctan to solve for theta here. Nope. Arctan is always between negative pi over 2 and pi over 2. Theta is not in any way constrained like that. So you can't solve for theta here either. Let me show you the kind of trouble you can get into if you ignore these points. Let's think about this point right here, -1, -1. Again, rectangular coordinates, unique, no problem there. Excuse me. So what can we say about this point? Well, I can plug into these equations and come down here. I know r squared is 2 and tan theta is 1. Now, if you play, like I say, fast and loose with this, you would just say, okay, well, that means that r is the square root of 2. And this ought to mean that theta is pi over 4. And if you look at these coordinates, 2 comma pi, square root of 2 comma pi over 4. That puts you up here, and that's the wrong point. So, absolutely wrong answer if you're sloppy on this business. Does everybody see what went wrong? Everybody see how that's bad, right? So you've been warned. Be really careful with this kind of thing, and in general, I think the good advice is always think through the geometry. Always look at the picture. Don't try to have a set of formulas and or rules that will do your geometric thinking for you. It's a bad idea. It's extremely prone to failure at best. Right? Think about the picture, right? Think about your options, and then just make reasonable choices. So, for example, this equation, what it really tells me is that r is plus or minus the square root of 2. This equation right here, what it tells me really is that theta could be any of these values, and the 2 pi in is just a recognition that, well, of course you can go around as many times as you want. That doesn't matter. But we kind of have two options here for the angle. Whoops. The two options for the angle could be pi over 4, could be 5 pi over 4. Again, plus as many full turns as you feel like. Okay, so having written this down, now you have to kind of think it through, and you look at the picture and think to yourself, all right, well, what would happen if can I pick this and this? And you quickly realize that from the picture that, nope, I can't, wrong point. It just went the other way. So then you consider your other option. Maybe it's square root of 2, 5 pi over 4, and of course that gets you the correct direction, correct distance, and it gets you to the right point. And likewise for the other pair. Everybody good? All right. Okay, moving along. Oh, they're giving me another. Boy, they're being rude about this. Okay, gotcha. Okay, equations and polar coordinates. Sometimes they're pretty straightforward. This first one here is kind of a freebie. R equals 3. You don't even really have to convert this to understand what this is. This is telling you distance from the origin, right, is 3. And if the distance from a given fixed center is always a constant, that is the definition of a circle. So, boom, circle. Easy. But if you hadn't noticed that, notice you could reason that through with some algebra instead. Square both sides. Recall that r squared is x squared plus y squared. And boom, previously known rectangular equation for a circle. Yeah? All right. Ditto here, angle given and fixed. Well, that means we have a direction, and of course that means all of those vectors, and of course for negative values of r, all of these other vectors, and so you pretty quickly get a straight line. But alternatively, and the move here is just different. Oh, every question is different. Here, the slick move is to take the tangent of both sides. And if you take the tangent of both sides, you get into this convenient situation where you can convert tan theta as just y over x. Again, previously known formula. Right? And then this is one easy move away from being, again, the equation of the same straight line. All right, now here's a tricky one. What do you do with this polar equation? Sometimes there's just nothing there's no algebraic tricks that you can play that will turn your equation into something that you recognize, rectangularly. And sometimes you have to just take a deep breath and plot a bunch of points. And that's what happens here. So here we go. What I'm going to do is I'm going to break up my angles into chunks. I'm going to start by thinking about theta going from 0 to pi over 2. We'll plot that part of the curve, and then we'll move on to the next angles in a minute. But theta, 0 to pi over 2. Now do be careful. Theta is not the argument of sine. The argument of sine is 2 theta. That means 2 theta is going to go from 0 to pi. And as the argument goes from 0 to pi, sine starts at 0 and then goes up to 1 and then comes back down to 0. And now you just have to think that through as your angles, as you start from angle 0 and move around to vertical, right? So from 0 to pi over 2. Apparently r needs to do this move where it starts at 0 and goes up to 1 and then comes back down to 0. And if you draw that out, that gives you a curve that looks like this. How we doing? Everybody follow me? And then you can repeat. Let's think now about the next range of values. We just looked at 0 to pi over 2. Now let's look at pi over 2 to pi. And again, keeping in mind, this is what theta is doing. Theta is not the argument of the sine here. It's 2 theta that I'm going to be taking the sine of. 2 theta goes from pi to 2 pi. During which time R goes from 0 down to -1 and then back up to 0. And so now this one's a little harder to draw. Keep in mind we're going to be looking at angles that are like that, right? And to those negative angles, we're going to be looking at, to those angles, we're going to be looking at negative values of r, so we're going to be going backwards. And as the angle goes from there to there, the backwards of the angle will go from there to there, you might say. Right? And so then keeping this in mind as a guide, what we're going to have then is starts at 0, and then it goes negative, gets all the way down to -1, and then it starts increasing back up to 0. And so the curve does that. Right? Keep in mind, so initially the curve did kind of like this. And now it's sort of continued on in a kind of a continuous way, right? I mean, it's doing like that. And you might speculate that it would continue like this, and then it would continue like that, and then loop back up to where it was before. And you'd be right. That is what happens. This is good exercise, though, and I want to leave that part as an exercise for y'all to flesh out on your own. Think about what happens for these values of theta and for these values of theta. All right. Everybody good? Just, practice if you would like to have some. Okay, couple of algebraically convenient examples. This one's really nice. R equals cosine theta. This reminds us of that first example we saw at the top of the page where we had an R, and we like R squared because, of course, obviously we like R squared because, we know stuff about R squared. So there's this temptation to square both sides of the equation, just like we did previously. The problem is that cosine squared is nothing convenient in rectangular coordinates. So the clever move, I wish I thought of it. I didn't. Somebody showed me this. Clever move, don't square both sides. Multiply both sides by r. You still get the r squared that we wanted. But then multiplying by r, the right side turns into something else that's convenient in rectangular coordinates. And so we have successfully converted a polar equation now into rectangular. And what you do with this rectangular equation, well, now it's just algebra. It is, however, algebra that I think is worth commenting on. A lot of students have, it's been a while, right, since what they used to call Algebra 2 back in my day. I'm sure they call it something else now. But completing the square, this move. Make sure you can do completing the square. A lot of students have kind of forgotten how to do that, or rusty on how to do that. And I'm not going to say it comes up every day, but it does come up, and it's when you need it, completing the square is very handy. So you get this, which we recognize as the equation of a circle. Okay. And you can take it the other direction sometimes, where we have rectangular coordinates equation, and we convert that into a polar equation. This is actually easier. You pretty much just start plugging in. You don't really have to do much trickery in most cases. Now there is one little tricky move that I think is nice. If you take this square and expand it out first, don't plug in immediately. Right? Expand out that square first. That gives you the opportunity to recognize what you might not have seen in the original form of the equation, that there's an x squared plus y squared kind of hidden in there. Right? And that x squared plus y squared, instantly you can write that down as r squared. You don't have to take the x and call it r cosine theta and then square it and then likewise y, and then you factor out the r's and you recognize the trig identity. I mean, not that it can't be done, it's perfectly doable, right? But it's easier to capitalize that it's kind of already been done. And then, of course, y is r sine theta. The ones cancel, and then canceling common factors of r, moving some things around, you get r equals 2 sine theta, which we already knew that this was a circle, but now we have the polar equation of that circle. Everybody good? Okay. All right, and I have 12 seconds left. I'm not going to get anything useful done there. Let me just say welcome back. Hope you all had a good weekend, and see you on Wednesday. Have a good one.